I am present here again today to discuss some important topic of physics under the heading Physics Made Simple or Physics Made Simplest. So I am now discussing today, as written here, nucleus becomes known after the Bohr's theory. I completed long back Bohr's theory where I explained all spectral line emission etc. And then now from the atomic side we go now to the nuclear side. That is, the nucleus becomes known. You remember that the Rutherford and his group, they performed some experiments using alpha particle source. That was the scattering of alpha particle from metallic foils. They used a gold foil and radium alpha particle source supplied by the Curie group. So Curie group supplied alpha particle source to various laboratories, but it was the Rutherford that the Rutherford group performed experiment on alpha scattering. And what was the result of alpha scattering? Large angle scattering of alpha particle. That is, alpha particle scattered, some alpha particle scattered straight, some with slight angle, some slight more angle, some at more than 90 degree, some came more than 120 degree, and very few came back also, just nearly 180. So that was the backward scattering of a particle. That is it means there was a high force, repelling force, which repelled alpha particle. They couldn't penetrate inside. They reached up to a certain distance. That was termed as the distance of nucleus. Means nucleus is now known. Nucleus becomes known. What is the nucleus? Nucleus is the central part of the atom. That is, we have seen the Bohr atom. So this is the central part of the nucleus. And then outer we have orbits. So this is the central part. That is, when we sent alpha particle, Rutherford scattering, they came back, that alpha particle beam. So this was, they could reach certain distance. So that was the distance of closest approach of alpha particle, where the kinetic energy of alpha particle, E alpha, was equal to the potential energy. And this E alpha, kinetic energy of a particle, was equal to the potential energy that was Z square over 4 pi epsilon naught R. And that was E alpha, means 1 by 2 m and V alpha square, kinetic energy. And this was this distance R. This was the distance of least or closest approach of a particle. And this distance R was calculated using this equation, this kinetic energy and this potential energy. From this, it gave birth to the nuclear size. So nuclear size which was estimated by Rutherford experiment by Rutherford group, Geiger, Marsden, etc. And they got the idea of nuclear size, that this R was equal to term as the nuclear radius. So this gave the alpha particle scattering of Rutherford gave birth to nucleus. So nucleus becomes known. And this alpha particle scattering or Rutherford experiment gave birth to nuclear physics. Nuclear physics came from the Rutherford experiment. This was nuclear size, the estimation of nuclear size from. So what is now nucleus? A nucleus is now, you say, that was known, the charge discovered and the electron discovered, the proton discovered, Nucleus means protons plus neutrons. And atom means nucleus plus electrons. We have discussed already about the atom, that is the Bohr's atomic theory or atomic structure, etc. Balmer series, Pasteur series, Fund series, Lamin series, etc. That was the atomic spectra. And now we are talking about the nucleus. The nucleus becomes known. Nucleus is nothing else but protons plus neutrons. Well, we have, say, now let me say some problems we will talk about that. Say how many electrons how many electrons protons and neutrons are there in 12 gram of say carbon 12 and 14 gram of carbon 14. Carbon 14, carbon 12, these are two isotopes of carbon. So if we take a sample of carbon 12 having 12 gram mass, so how many protons, electrons and neutrons are there? Estimation of that. Or if we take 14 gram of carbon 14, how many neutrons, protons, electrons will be there? So we want to estimate this thing. What we should do? So that we get an estimated number of protons, electrons, neutrons, etc. So let me tell you to get some idea of number of protons, electrons and neutrons in these samples, what we should do. You see, mass number or atomic weight, all these terms you know. Atomic weight of carbon is 12 and for carbon 14 is 14. So therefore we will get from Avogadro number, from Avogadro's number, we can get estimation of all these things. What we know, Avogadro number, that Avogadro number, is 6, nearly 6 point something, but I take 6. 6 into, say, 10 to power 23. 6 into 10 to the power 23. This is the Avogadro number. This much number of electrons or atoms, you can say atoms, you calculate this. How you calculate this? This is equal to how much? 6. And you have how much? 12 gram. So Avogadro number. This number represents the number of atoms in one atomic weight. And we have 12 gram, or for carbon 12, so this is one atomic weight, 12 gram. So this means these are the number of atoms, Avogadro number for number of atoms in one atomic weight. And you know in one atom how many electrons or protons are there? There are 6. So you can say that 6 is the number of protons or number of electrons, equal number of protons. So 6 into Avogadro number. This becomes the total number of protons, number of electrons, or also protons, because proton number and electron number is same, because charge is the same. So this becomes 6 into 6, 36. 36 into 10 to the power 23 protons, also electrons. If this is one atomic weight, because one atomic weight means so many atoms in one atomic weight, Avogadro number. So this becomes number of protons. And you see what is the number of neutrons you can get, because number of neutrons is simply how many neutrons are there. You simply get A minus Z, where this is the number of protons, this is the total number of, this is atomic number, atomic weight. So from this you can find out A minus Z, that becomes total. And it means whatever A minus Z is equal to Z, that is the same number, neutron number, that is the neutron number. Z is 6, A is 12, so 12 minus 6 is 6. So same number, N is also 6, as the electron is 6 in the one atom. So you have a number of electrons, protons equal to this, and for carbon 12, number of neutrons also equal to same. So number of neutrons is also equal to how many? 6 into 6 into 10 to the power 23 in one atomic weight. This was in one atom, number of neutrons in one atom. So 6, so this becomes a number of neutrons, that is 36 into 10 to the power 23 in one atomic weight, that is in 12 grams of carbon 12. Similarly, this becomes also for carbon 14, we can get same number, because now carbon 14 becomes, there is here 6, there is 7, so it becomes more, that is for carbon 7, this becomes multiple by carbon 14 means 6, carbon 14 means proton equal to electron equal to 6, neutron in one atom equal to 14 minus 6 equal to 8. That is in one atom. So number of protons or number of electrons or number of neutrons in one atomic weight, that is 14 grams of, in 14 grams of number of protons in 14 grams of carbon 14, that is, proton becomes 6, so that is 6 into 6 into 10 to the power 23, that is 36 into, you can imagine that in one atomic weight of 14 gram of carbon 14, this is the number of proton. Proton also electron, because electron proton number is same. But the neutron number in one atom of carbon 14, 8 neutrons are there, so number of neutrons. number of neutrons in 14 gram of carbon 14, that is the atomic weight, becomes, number of neutrons becomes 8 into Avogadro number, that is the 48 into 10 to the power 23. So these are the neutrons. These were the protons and electrons, and these are the neutrons. So you can get an idea that how many neutrons are there in one atomic weight of carbon 14. So that is the idea of nucleus. The nucleus means combination of protons and neutrons. And you see that just like the carbon, I have given an example that carbon 12 and carbon 14, how many neutrons are there or how many protons are there? 36 into 10 to the power 23, or in carbon 14, 48 neutrons, 48 into 10 to the power 23. Now we have some idea about, say, what the one definition, mass 1 AMU. What is 1 AMU? 1 atomic mass unit. You know, atomic mass unit we define in terms of the mass of the one atom. That is hydrogen, you can say. So that is 1 AMU as per definition. 1 AMU is 1 by 12 of mass of one carbon atom of 6 carbon 12. 1 by 12 of this, because it is the standard definition from, earlier it was from oxygen, but now it is from carbon. So that you can see, by definition, we have the mass of one carbon atom, then divide by 12, we get the definition, this 1.66 into 10 to the power minus 27. That is one atomic mass unit. This is so many kilograms. This is the definition. One atomic mass unit is this much. And let us see that from a size of the nucleus, what the order of size of the nucleus? Size of the nucleus from Rutherford alpha scattering. And in the beginning I told you, I wrote that 1 by 2 mass of alpha particle, velocity of alpha particle, that is kinetic energy, is equal to the potential energy, that is Z E square over 4 pi epsilon naught R. This R is the size of the nucleus. From this you can estimate the value of R. You get what is the value of R. So, or the notation, maybe D or R, whatever you want to write. 1 by 2, this 4. So R is equal to, we can get R is equal to, this 2 cancel here, Z E square, this upon 2 pi epsilon naught. R comes here, this 2 is cancelled here, and then mass, this comes here. So this gives the idea of size of the nucleus. And now we put this Z also, alpha particle, for alpha particle. This is equal to 2. We put this here. So R is the nuclear size. is equal to, simply we put this here 2. So 2 is cancelled here. So that E square divided by pi epsilon naught m alpha b alpha square. So remember that this was earlier the estimation of nuclear size by the Rutherford group. But that was, you see, depending on the velocity of alpha particle. If you take alpha particle from a source of higher energy, B alpha becomes more, then R decreases. So it means R depended on the alpha particle energy. How much distance? In fact, this was the measure of distance of closest approach to the nucleus. The distance between the incoming alpha particle and the nucleus. And that was defined as the nuclear size, which was not very correct. Very correct, because if you increase the energy of alpha particle, this distance becomes less and less. So, estimation of nuclear size from alpha decay and alpha scattering experiment was not telling. Alpha decay was giving a much smaller radius, while alpha scattering was giving large radius. Because alpha particle radius measured by alpha particle scattering depended upon the velocity of the alpha source. You take higher energy 6 MeV alpha particle, if it is available from some natural sources, you will get less distance. So this way R was the classical radius of a nucleus, which was depending upon the velocity of alpha particle, and as per definition this varied. In fact, this was measured by alpha particle of around 4-5 MeV. The distance was about 60 Fermi, 60. But alpha decay from uranium-238 gave the estimation of alpha particle. Alpha particle scattering gave 60 Fermi, while the other experiment gave 30 Fermi. That was varying with high energy alpha particle source. Alpha decay gave much smaller radius, that was about 10 Fermi, alpha decay. So this estimation of R was depending on the source energy, and using the source of 4-5 MeV we got 60, then using the source of 6 MeV we got 30, but alpha decay gave the estimation of nuclear size from uranium-238. Alpha decay gave around 10 Fermi, 9 point something, so 10 Fermi. So that was the true radius of nuclear measured by alpha scattering, alpha decay. They were not telling, they were not equal. Because the alpha decay gave from the inner, the radius estimation from the potential energy of alpha particle and alpha particle kinetic energy which came out from the nucleus. But alpha scattering gave the estimation of nuclear size from the kinetic energy of alpha particle. So this is the estimation of size of nuclear radius. For example, you see this has measurement of R is about 32 into 10 to the power minus 15 meter. It was for probably for gold foil, about 32 Fermi, that is 32 Fermi for gold. This was for scattering, alpha particle scattering from the gold foil. And the estimation of this, you see, we have from the alpha decay we have about from the estimation of nuclear size for silver, for gold, for silver, from the silver foil scattering we get R is equal to about 20 Fermi. In this way, radius of various different elements, foils were measured by alpha scattering experiment using Rutherford setup, and they got an idea of that nuclear size R is given by a empirical formula that R is equal to R naught A1 by 3. What A1 by 3, A is the atomic weight, R naught is a parameter. R naught was about 1.2. In value was taken 1.2 Fermi. Or A was atomic weight. So this was the relation obtained from the various measurements that R people measure. This R is nothing else but the R, nuclear radius R. You see that we have volume of the nucleus. Volume is 4 by 3 pi r cube. Volume of a sphere. R is the radius of a sphere. So 4 by 3 pi r cube, and this is the R, radius. So volume is 4 by 3 pi, and r cube means r naught cube and A. This is also from this relation also is from, because this is a constant. So volume is proportional to A. As A increases, volume increases. So volume increases means size increases, that is radius increases. So this radius, this radius and this volume, they gave idea. Or from this idea you can get this idea that volume is proportional to A, and volume is proportional to, we have here R 4 by 3 pi r cube. So r cube here. So r cube is proportional to A, or R is proportional to A1 by 3. You can say like this. So that way, this proportionality constant, we got R is R naught A1 by 3. Because volume is proportional to atomic weight. More weight means bigger size, volume increasing. So now we have idea of nuclear size, we have the nuclear volume, we have. Now you can see what the nuclear density is. What is the nuclear density? Nuclear density, what is the nuclear density? From the mass and the volume. Density, you know, density is equal to mass upon volume. So nuclear density, how you can estimate nuclear density? The nuclear density, you write D or by any other symbol. You write by rho, you can write any symbol. So rho is mass upon volume. Well, what the mass and what the volume? How you write? That rho is, or rho of the nucleus, you can write by a nucleus, density, nuclear density. Nuclear density we can write as rho n. This is simply mass. Mass, how much mass? How we write mass? Say A is the atomic weight, and say m is the mass of one atom. Then A into m is the mass, total mass, and AM, and then volume 4 by 3 pi r naught cube, and A. So this is m is the mass of the one particle of the atom, that is the proton or neutron. We take mass of proton, neutron equal. So m mass of the proton, A is the number of total proton and neutron. So this is, m is nearly, we take nearly equal, but n mass of neutron is slightly more, but we are taking say nearly equal. So this is the total mass of the atom, and this is the volume. So we can get A is cancelled. The density of nucleus is m over 4 by 3 pi r naught cube. A is cancelled. What the m is the mass of one constituent of nucleus, the neutron or proton. So this way you can write the nuclear density, how much? Well, this 3 you can write upside, so 3m over 4 pi r naught cube. So nuclear density rho n is equal to 3m. What the mass of proton? 1.67 into 10 to the power minus 27 kilogram. Divided by 4 pi r naught cube. Well, r naught cube means 1.2 and Fermi, and 4 pi means 4 into 3.14 into r naught cube means 1.2 into 10 to the power minus 15 because it is Fermi, and that is the cube. So this gives you the nuclear density. You can calculate the nuclear density rho n is equal to, you solve this, multiply and solve, you will get 2.3 into 10 to the power 17 kilogram in the kilogram, and r is the Fermi, you have down is the Fermi, which converted into a meter cube, because this is now meter, 10 to the power 15 meter. So this is the density of nucleus, constant, 2.3 10 to the power 17 kilogram per metric cube. So this nuclear density is constant. You can say that the density, mass density for element to element changes. Lead is very much dense, mercury 13.6, much more, like that. Brass, copper, iron, all elements density changing. But here the nucleus is made from neutron and proton. So that is the constituent of nucleus. Nuclear density is constant for all elements, it is not depending on the element, because it is depending upon the number of neutrons and number of neutrons, protons. As number of neutrons, protons increases, that is the size also increases. So radius also increases, means volume. Accordingly, as the nuclear mass increasing, our volume also increasing. So mass upon volume remains constant. That is the nuclear density. So nuclear density is a constant number. You see, this constant nuclear density gives another idea of a property that is called saturation. That means density will not increase, density will not decrease. You can change the nucleus. You see, density, metal density changes, the metals, because that is the made from number of neutron, protons, number of nuclei. How many nuclei are made in the copper, how many nuclei are in the iron. So that changes the density. But here, density depends upon the nucleons, that is the neutron and protons. So that is the constant thing. Nuclear density is not varying with the element, it is constant. Because it is the density of nucleus. That is the nucleus of different element may have different number of neutrons and protons. But as the mass increases, the size also increases accordingly, proportionally. So this ratio remains constant. So this is very important. This gives an idea of saturation. And this will give, when you will read the nuclear forces, you will get a property of nuclear forces that is called saturation. So saturation is from saturation of nuclear density, and that is the nuclear density is constant. It is not depending on element to element. It depends only on the number of nuclear constituents and the nuclear size. So the ratio is constant. Now we have, say, Now we will talk about a mass defect. Mass defect, and we will talk about binding energy, conceptual things, that what the binding energy is, what the mass defect is, what is the observation, from where this mass defect came, from where this mass binding energy came. So let us talk about something about that. What the mass defect is, you see one proton plus one neutron. You see, this becomes combination of one proton, one neutron. What this is called? This is called deuteron. Deuteron is hydrogen, heavy hydrogen. That is one charged proton and two mass, one H2. One H2 is the deuteron. This is the deuteron. And one H1 is the hydrogen atom. This is the deuteron atom, this is the hydrogen atom. Now, deuteron atom has got two, one proton plus one neutron. What is observed is mass of deuteron, this is less, as observed. Mass of deuteron is less than how much? What? Mass of deuteron is less than one proton plus one neutron mass. Means you have separate mass of proton, separate mass of neutron. You add these two masses, you get mass of deuteron. But it is found that mass of deuteron means 1H2 is less than mass of proton, one proton plus one neutron. This is mass is less. So this is a strange thing, that when you are combining nucleons, making the complex nuclei, you get the mass of the complex nucleus is less than the mass of individual number of nuclear constituents, that is the protons and neutrons. Well, this is a strange thing. Why a strange thing? How to explain this thing? So this thing is called mass defect. Means mass of this is less, this is more. So this mass of proton plus mass of neutron is more than mass of deuteron. So this Mp plus Mn minus Md is the loss of mass. Mass defect. That is, we write by delta M. Delta M mass is lost. When these two constituents of deuteron, proton and neutron combine together to make complex thing deuteron, we get some mass disappears. That is, mass is lost, or that is called mass defect. Mass goes where mass goes. When we combine one proton, one neutron to get deuteron, some mass is converted into energy. That is the mass loss. And when you want to break this deuteron into its component, constituents, proton, neutron, how you break? You have to supply some energy. So you give energy so that the proton neutrons are separated and we get separated proton neutron. So how much mass is lost when they combine to give you deuteron? You have to supply same energy so that that energy goes in the breaking the deuteron and we get separate mass proton neutron. It means that energy is converted into some mass, which mass is added here, so that this is less than this. How much less? You supply the energy to break this. And that is from Einstein's mass energy equation. Important relation, that is E is equal to mc square. That this is the mass m converted into energy. Because energy and mass are interconvertible. So energy is converted into mass, this much mass. Or this much mass, if it disappears, if total mass is converted into energy, this energy is produced. So that is the equivalence of energy and mass by Einstein's energy-mass relation, that E is equal to mc square. So this mass defect here, or mass disappears when we get a complex nucleus from the individual mass of proton neutron. We get some mass lost, and that mass lost, or that is a delta m here for the deuteron. This delta m into c square converted into energy. So that energy is evolved or disappears, mass disappears, and you want to break the system, you have to supply energy. So that energy converted into mass. That is the mass defect. It means all the systems, all the nuclei are bound. The systems are bound. And when you want to break them, a complex system, energy is to be supplied. So energy is supplied, then energy E delta mc square. So the mass defect is converted into energy. Mass is when we make system, compound system, complex system, mass disappears as energy. When we want to break this complex system, we supply energy, that energy converted into mass. And that mass again becomes equal to mass of the constituent. So that is the delta m here, mass defect. So that is the, for any system, delta m disappears. Delta m is equal to z number of proton, mass of this, plus a minus z. This is the number of neutrons and the mass of the neutron. This protons, this neutrons, total number, and this delta m which disappears. And this is this minus mass of the atom, the combined system, and that is the nucleus, minus z of that is the number of z, and E means electron mass. You separate out atom. From atom you remove the electron mass, that becomes the nuclear mass. So this is the constituents mass, this is the nuclear mass. Because atom mass minus electron mass, Z. So we are neglecting the binding energy of electron. That is almost very small. Because this is the mass of the constituents, and this is more than this. So this is the mass defect. And in terms of energy unit, you have c square multiply here, and then you have c square multiplied here. That becomes the energy unit. This is the mass defect. Now you can see that now I give you an example from one example from mass of alpha particle. From mass of alpha particle, I give you one example that alpha particle is made of 2 proton plus 2 neutron. I add all this 2 proton, 2 neutron. This mass is equal to about 4.0330 unit, atomic mass unit, AMU. And what we observe is mass of alpha particle is measured. This is 4.0026. So this is the mass of alpha particle as measured. This is the mass of 2 protons plus 2 neutrons. So you can see that mass defect, delta M, when alpha is formed, becomes, you have 4.033 minus 4.0026, and this you can subtract, you will get 0.0304. So much, that is the atomic mass unit. And from the definition of one atomic mass unit, which I have not given, I have not calculated in fact, from one atomic mass unit, you convert into energy by E is equal to mc square equation. That is the, from atomic mass unit, one atomic mass unit, you have 931.5 MeV. That is, you have the mass in terms of the, that is the 10 to the 27 kilogram, and then c square multiplied by c square, you get this relation. One atomic mass unit is 931.5 MeV. So you can get this delta M for alpha, mass defect for alpha particle, that is a 0.0304 into 931.5 MeV. So how many MeV? Multiply delta M alpha is equal to about 28.3 MeV. What does it mean? When alpha particle is formed by the combination of 2 protons and 2 neutrons, there is a mass defect. Mass disappears. Mass lost. What is the mass lost? In terms of mass, this much kilogram. In terms of energy, 28.3 MeV. So that means when 2 proton and 2 neutron combine to make alpha particle, 28.3 MeV energy is evolved. So much energy is produced. From where? From mass loss. Mass disappears, so that mass converted into energy. How much? One alpha particle is formed, 28.3 MeV energy is produced. That is the mass defect. Mass loss gives you the energy. So this much energy is available when alpha particle is produced. That is the 28.3 MeV energy. So what you can get? This much energy is produced when 4 nucleons, 2 protons, 2 neutrons combine. So what is the total binding energy? That is the binding energy means 4 nucleons, 2p plus 2n, combine together, you get this much energy. So we have binding energy term. What is the binding energy? Binding energy B, we can write. B binding energy is the total energy which keeps the system bound. Means alpha particle is bound. You want to separate. This much energy produced. This much energy is lost. So when you bind 2p and 2 neutrons free, alpha particle you want to break, well, you have to supply how much energy? This much energy which was evolved there and which disappeared. So you give this much energy to alpha particle, it means you can break this into 2p and 2n system and you will get alpha particle converted to 2 proton and 2 neutron. So that is the binding. And one system is bound by the binding energy means how much energy is lost when the system is produced, complex system is produced. And then there is binding energy. One is the binding energy per nucleon. That we write by B bar. B bar is equal to B over A. Means you divide the total binding energy by number of nucleons, total number of neutron protons A. So that becomes binding energy per nucleon. And remember that binding energy for I give some example, for iron is about 492.8 MeV. Means when iron 55 or 56 is formed by combination of neutrons and protons, so much energy is produced. It means you want to break the nucleus of iron into its component neutrons and protons, you have to supply this much energy to the system to break the iron into different its number of constituents, proton and neutron. Similarly, binding energy for bismuth, that is the very heaviest system, is about 1640 MeV. It means when bismuth is formed by combining, you see bismuth is how much? Bismuth is 83 and how much? 209? 83 bismuth. Maybe 83, 82. Bismuth maybe, I don't remember exactly, maybe 209. 83, I have 82 lead, that is 82 lead, 82 PV, 126. 126. Lead is doubly magic, it is 628, 208. So lead is 82, 208, bismuth is 83, 209. This is all correct. So for bismuth, this is about this much. Means bismuth has got 209 number of nucleons total, 83 protons and 126 neutrons. 83 protons and 126 neutrons, total number is 209. So 83 protons plus 126 neutrons make bismuth nucleus, and this much energy is produced, is lost in the nature, it goes in the nature. So when you want to break bismuth into its components, 83 protons and 126 neutrons, separate, you have to provide this much energy. That is the meaning of binding energy. The system is bound by some energy. You cannot make it separate. To make it separate, you have to provide this much energy. That is the meaning of binding energy. And binding energy per nucleon, you can calculate from the mass defect, from the difference of, you measure the masses of different elements and you know the mass of constituents, that is the proton and neutron. You can find out the binding energy and you can get the binding energy per nucleon. So binding energy per nucleon is plotted for different nuclei in terms of A, value of A. How the binding energy per nucleon? We calculate is we get a graph like that. You see, how we calculate that B bar for iron, for bismuth you get for iron, B bar is equal to total binding energy divided by 492.8 MeV divided by the number of nucleons. Iron has got 56. So this gives you 8.8 MeV. That is B bar for iron. B bar for bismuth, you calculate is 1640 divided by 209 number of proton neutrons, then B bar is equal to about 7.84 MeV. So that way binding energy per nucleon, B bar, you can say iron, it is maximum in the middle and it decreases. So I have here a plot of B bar versus A for different elements, and from starting from here, this is the curve which represents, here is the maxima. Maximum values around iron, say around maybe 8.8. Here on this side is about 7 bismuth 7.7 point something. Here it is last stable uranium. This is the bismuth. So for it is about you can say 7.4 or something like that. Maybe here 7.8 like that. Increasing. Here it is, say binding energy, there are dips here. These are the systems alpha multiple. Means you have A is equal to N into mass of alpha. Means you have 2 into mass of 4 into mass of, like that. You have, say, starting from, say, suppose alpha particle helium-4. Helium-4. You have then beryllium-8. You have, say, 12, carbon-12. You have, say, oxygen-16. You have, say, neon-22. You have, say, magnesium-24. You have, say, silicon-28. You have, say, sulfur-32. You have, say, chlorine-36. You have, say, calcium-40, and so on, like this. So all are multiple of alpha 4. 4, 2, 8, 3, 4, 5, 6, 7, 8, like that. So all these systems are made of multiple of alpha, and they are more strong, means they are more strongly bound. So these dips represent maxima of energy binding. Maxima come down, maxima. So these are these multiples of. So at the lower side, this is the 0, and this binding energy B bar like that. You see that around average value of of B bar is about 8 MeV. Maximum 8.8, minima 7.4, here few nuclei low. So average is around 8 MeV per nucleon. Means you want to separate one nucleon, then the average energy required to separate the one nucleon from the nuclei is around 8 MeV. So here these dips are systems of alpha and multiple, means more stronger. And here we have the deuterium, tritium like that, low binding energy, alpha particle something about 7 point something here. And then these are the medium iron like iron, tin, etc., more bound systems, and these heavy nuclei, and uranium 7.4. So this represents the binding energy. This is called binding energy curve. That how binding energy depends upon the mass of the nucleus. So this is the binding energy curve. We have some important observations or a conclusion from the binding energy curve. What are the important observations of binding energy curve? What are important observations? One important observation of binding energy curve is that the maxima is about 8.8 MeV. That is iron, near iron. Maxima is, that was we saw for iron. Maxima is about 8.8 MeV. For iron, 56. The iron nucleus is most tightly bound. That is, the iron nucleus is most tightly bound, and most tightly bound systems are more abundant in nature. Because less tightly bound, they break and they disappear. But you see in the nature, more iron is there. That is because iron is most tightly bound. And what we observe the saturation also, means in the binding energy curve we get saturation is there, means B bar is nearly constant for the medium nuclei. And so this is called saturation. And what we see, binding energy B bar is decreasing with A. Why it is so? Because as A increases, more number of protons increases, so more repulsion. More repulsion means systems are less bound. So as we go to heavier nuclei, you see very heavy nuclei, they are not available in nature because more breaking forces, means repulsive forces or protons. That is, the protons are repelling, the systems are not bound. So as B bar increasing, the binding energy, as A is increasing, binding energy is decreasing. that the systems are not stable. Heavy systems are not stable because repulsive forces are more strong. So that decreases. Okay. Now we talk some another thing here. You get the systems evolved, systems from how the systems are evolved. So we get, you see, idea of what the Q value. What is the Q value? We write a reaction that is 1H2 is producing you interacting with nitrogen 14. This was the Rutherford experiment also. 1H2 means deuterium, a beam of deuteron. Deuterium interacting with the nitrogen nucleus. We get a system which is a carbon, 6 carbon for 12, 7, 8, 6 carbon 12 plus 2 helium 4 means 6 plus 2 8, 7 plus 1 8, 2 plus 14 18, 12 plus not 2 helium 4. So 14 plus 2 16, 12 plus 4 16. Okay, good. So mass conserved and proton number conserved. So this equation is right. A deuteron beam interacting with the nitrogen nucleus, we get that this is called a nuclear reaction. Nuclear reaction generally started by deuteron beam on nitrogen, we get carbon and alpha particles produced. So production of alpha particle by some nuclear reaction. This is not natural alpha particle, this is the alpha particle produced by the laboratory by deuteron beam using some accelerator. So let us see this reaction. Here we write that masses, we write these masses here. This mass is 2.0141102, this mass. And then this mass is 14.003074. So these two masses together we get by adding 16.017176. On this side we have carbon 12, the mass is 12.00. And this side we have alpha particle mass 4.002602. We add these two together, we get 16.002602. You see this mass on this side, this mass on this side. See the difference. It is 26, it is 01, it is 00. So this is more. So difference is, difference of mass is how much we differentiate. We subtract 0.014574. This is the atomic mass unit here. But remember, this is more than this. So we write this as the minus because this side is less. This is the production after that. This is the initial system has more mass. This is more. So we get deficit and means mass deficit, mass goes on. This is less. This mass disappears as the energy. So this is how much? You convert this into multiply by 931.5 to get MeV, and this comes out to be 13.576 MeV. So this interaction, production of carbon alpha particle by the deuteron and the nitrogen reaction, we get this much energy difference, means deficit of energy. This much mass from mass, this much energy is lost. So the energy is required to balance. To balance this energy equation, you have to give this much energy here so that this becomes equal. So means 13.56 MeV energy is required to make energy balance. What does it mean? Well, this reaction is not possible at the zero energy or the low energy. You have to provide, because this side is the less which we are getting. This is more. This is lost. It means that this energy, this energy. This energy is more. So this is more in this side, the positive, this is less. If this is more, this becomes negative. So let me say that this much energy evolved. This energy evolved, produced. It means this difference of energy is called Q value. Q value is the difference of this, means Q value is the mass of the here, initial masses minus final masses. Initial mass minus final mass, Q value. This Q value is positive, means here Q, positive. Energy is produced in this reaction. Energy is evolved. So this reaction is possible without supplying any energy, because Q is positive. So what is the meaning of Q value? Q value is the energy difference of two sides of the interactions, initial reactions and final products, the difference. If this becomes negative, well, this reaction is not possible unless you provide the energy. Here the energy is positive, means this is produced. So this reaction is called endothermic reaction, means where the energy is positive, Q is positive. So Q is positive means exothermic. Q positive, exothermic reaction. Exothermic reaction. Q negative, endothermic. So there are some interactions where Q is positive, means energy difference is positive, they are called exothermic. They happen without supplying any energy, and they are reactions which Q is negative, they are called endothermic, means you have to supply the energy so that reaction starts. So this is the difference of the reaction. I can give one more example to make the easier thing to understand. So I give you one more example. That example is one reaction 2 helium-4. A reaction is started by alpha particle, that is alpha particle. And starting with the 7 nitrogen 14. Earlier we discussed deuteron reaction, this is now alpha particle reaction. And here we get the products are 8 oxygen 17 plus 1 proton. Alpha particle reaction on nitrogen gives you proton and the oxygen. 8 plus 1, 9, 7 plus 2, 9, 4 plus 14, 18, 17, so reaction is balanced. And now we get the masses here. This mass is 4.00260, 4.02, and this mass is plus how much? This is 14.00373074. You add these two, so mass of this is added together 18.005676. This side we have mass of the oxygen 17, 16.99 and 9133, and this we have mass of proton as 1.07825. This together gives us the mass of the system 18.0069 and 58. So mass defect. You have the mass difference or mass deficit. Mass defect, mass deficit, you can also say. Difference of mass you get is 0.00. This is 0.005, 0.006. So this is more. So this becomes minus. This is now minus. This thing is more. This is, initial thing is less, final thing is more. So this becomes minus. And multiply by the 931.5 MeV, you get this is equal to, multiply this is 1.194 MeV. What this means? That this reaction here, this Q, is negative. Means this is minus 1. This reaction is endothermic. First reaction was exothermic, this is endothermic. Means this Q is negative. This reaction cannot start unless energy is supplied. So this energy has to be supplied, only then the reaction is possible. So such reactions are Q negative. Q negative. Q negative endothermic reaction, where reaction you have to supply the energy. Q positive exothermic reaction, where energy is evolved and they can start at the zero energy or the lower energies. So these types of reactions are endothermic and earlier was exothermic reaction, where the reaction, so these are the nuclear reactions I gave example of. You want to transform one system to other system from by alpha particle, they must have some energy more than this. Then they start reaction with the nitrogen, you get proton and the oxygen 17. So this reaction is possible by providing kinetic energy to alpha particle which is more than this. Otherwise reaction is not possible. So I will stop today here and may I start something and tomorrow or next time. So thank you very much.